it's not just about throwing AI to the problem. The real breakthrough comes from marrying physics with AI, as shown in these slides. Combine the predictability of physics laws and also the adaptability of intelligent agents. So physics bring credibility and safety. AI brings skill and intelligence. Together, they produce something new, which are the digital engineers, context-aware, explainable, transparent, and trustworthy solutions. So this is what makes our approach fundamentally different from general purpose AI companies or machine learning or data-driven approaches. We are building vertical intelligence rooted in the domain expertise and physical reality. These are not chatbot co-pilots. These are fully fledged digital engineers who can understand the system, predict what's coming in the engineering domain, and act accordingly. So in this journey, we actually started with Ida. In the next slide, our first AI-powered engineer is Ida, a digital drilling engineer designed specifically to help decarbonize the energy industry. So Ida supports operations in drilling and well construction by reducing emissions, improve efficiency during the production, and making it safer to deploy carbon capture and storage technologies as well. So at the same time, she enables the scale up of zero carbon solutions like geothermal energies, one of our to-do, by simulating underground conditions, optimize drilling operations in geothermal fields, and also adapting in real time. Ida is currently in her internship working together with some of the world's leading energy companies and learn from them to bring AI into this field, not as a bolt-on, but as a true partner in the operation in an ambitious team. So this is just the beginning as AI-powered engineers. As we move from SaaS applications to agent as service applications, our mission is to make AI engineers who can understand, reason, and act in real-world industrial systems. And as you'll see next, reinforcement learning is not just the tool, it's the backbone of the evolution to ensure continuous learning. It enables Ida to continuously learn and adapt to real-world outcomes, guided by both goals and constraints. Now I'll give the words to Resi, Ida's personal trainer, to show us how exactly such an AI-powered engineer is trained. Resi, it's all yours.
Yeah, thank you, Ji, for the introduction, and thank you for opening or introduce the word reinforcement learning for the audience, because that's going to be the main kind of topic that I'm going to talk about, which is RL, or reinforcement learning for AI engineers. So I'm going to start on what makes reinforcement learning different and why is it powerful in the context of engineering. We know that traditional machine learning is great and has been widely used at recognizing patterns in data, but it's mostly passive. It doesn't act, it doesn't explore, while reinforcement learning is fundamentally different. It learns through interaction. The agent or the engineers, the AI engineers, doesn't just predict something and move on, but it makes decision, sees the result, and then learns from that. And this loop of feedback and making decision happens thousands or even millions of times during the training. And what especially useful for engineering is that reinforcement learning doesn't just try to be correct in the moment. On the other hand, it tries to improve the overall performance across time, across the full operation of the context that you're currently working on. And this is critical when you're dealing with process where especially early decisions affect everything that follows. And finally, reinforcement learning doesn't rely on us as the trainer or as the user telling it what's right or wrong in advance. It will explore by itself, it adapts, and it discovers strategies that work, even in a situation that we didn't explicitly program the AI engineers or the agents to do so. And in order to build one, or to build an AI engineer or reinforcement learning agent, we basically need these three things. The first component, or the first thing that we need, is called environment. And we can think of it as a sandbox or a digital replica of the system or the process that we're trying to optimize. And it basically what defines the rules of the process, how things work, how they respond, and what feedback the agent will get. And of course, the second, we have the agent. This is the decision maker, the main subject, the learner, the one that makes decision inside the sandbox itself. And as I mentioned before, it explores, take action, and get feedback, and obviously gradually to improve its behavior, understanding about the process over time. And finally, is to connect both these two components is the interaction loop, and it should be defined as a clear flow where the agent receives a state or the information about the environment and then choose an action or make decision and then get some feedback in the shape of either a reward or it could be also a penalty if it's negative, and also transition into the next state of the environment. And of course, this cycle will repeat thousands or even millions of times during the training itself. And every reinforcement learning system, no matter how simple or advanced, is built on this core structure: an agent, an environment, and of course, the feedback loop that connects the two. And the first component, again, is the environment, the sandbox or the system where the agent learns from. And it has to fulfill these three things. Basically, it needs to be rule defined or consistent so that the agent could learn from a meaningful patterns, even if, of course, we know that randomness will be present in the real world cases. But then the second, in many industrial cases like the one that we have, drilling, but also other industrial cases, it must be aligned with real world physics. Because we're not just training a game bot or a game robot, but we're building an AI engineer that needs to respect an operational constraint or boundaries, also physical limits and other behavior. And of course, the more accurate and reliable the simulation, the more valuable the training will be. And finally, it is also important that the environment needs to be fast and scalable, because often, as mentioned before, reinforcement learning often requires millions of interaction between the agent and the environments. That means the environment must support acceptable speed of simulation and also ideally run in parallel, because without that, the training becomes too slow to be practical. In our case, I think my colleague, has introduced IDA as our first AI engineer for drilling. We rely on WellSim, which is a drilling simulator built from a deep domain expertise in drilling engineering, because it models key physical processes like pressure dynamics, fluid flow, and of course, mechanical constraints. And all of them are based on validated operational data and research. And that level of details and realism is what allows us to train AI engineers that learn strategies that are based or grounded on actual field behavior. And once we have a reliable simulation environment, which in our case is WellSim, it could be different in other field. The next step is, of course, to make it usable for reinforcement learning. And that means adapting it to fit a specific interface. The first requirement is that the environment must be, I would call it resettable, which means, as mentioned before, the training involves several millions or 100,000 interaction between the agent and the environment, meaning that it will need to be resetted from fresh or initial state before the agent could learn new things and then apply it into a fresh set of environment and then repeat. And the second, that it must be step-based. The reinforcement learning training procedures or proceed one decision or one action at a time. In the interaction loop that mentioned before, the agent takes an action and then the environment return a clear response in the shape of feedback and also the new state. And this must be done in one step that can be defined by the environment or the simulation itself. And what you see on the right is a very minimal example of how the code will look like. the environment should have two main functions, which is the reset method or reset function, and also the step in order to move to the next step. And these are the two main entry points that make learning possible. And of course, I acknowledge that in most real-world scenarios, the original simulation software isn't built to support reinforcement learning directly, because it is also a relatively new field to be used to train AI engineers. And it often lacks the interfaces needed to integrate with these training frameworks. And that's why the first step is usually to wrap or translate your simulator into something that the agent can interact with programmatically. And in our case, that means building a Python accessible layer, or it could be other programming language around WellSim, allowing it to respond to this two method or to these two functions, the reset and step calls during the training. And this adaptation is what turns a very complex domain simulator into a very usable reinforcement learning environment. And of course, the main subject of AI engineers is the agent itself. And I separated it into two main things that needs to be discussed. The first thing is what it does. Basically, it observes the current state of the environment, and it could be a set of numbers, a sensor readings, or any other representation of the environment. Then it chooses an action or makes decision based on what it sees and what it has learned from previous interaction. And lastly, it learns from the reward itself. After taking the action, it will receive a reward from the environment, which is a signal that tells it whether the outcome was good or bad, and use it to refine its future decisions. And what makes this possible is, of course, a few components under the hood of the agent. The first thing is the policy. It is a language in the reinforcement learning, but you could see it as the actual logic or a model that the agent used to select an action based on the state itself. And of course, we need a learning algorithm, which then updates this policy based on what the agent experiences. And lastly, we of course need to set an objective, which define what better is, or what we can see from the agent improving. It is very important to set this thing in front. And lastly, need to put a statement that the agent will not just reacting, because it will actively learning, adjusting its understanding and behavior over time, and of course aligning with the goals that we define in the first place. And when it comes to implementing the agent, we generally have two paths. The first is to use an existing library, which most of them are in Python languages. And these are libraries that are production ready, come with well-tested implementation of common reinforcement learning algorithm. And they also sometimes include built-in tools that you can use to log your training, save and load the checkpoint during the training, and also handling the evaluation and training loops. This will be a great choice if your problem or your process fits the structure of the library, but then it also comes with the limitation. If the workflow or the problem doesn't really match with the library expect, then you probably need to bend your code a little bit around it. But then you also have the second option, which is to write your own agent, which basically you need to start from scratch, creating a custom class of algorithm, which basically starts by understanding the basic concept of the algorithm itself, which are usually open source in lots of paper out there. But it gives you a full control of what you think important from your class. But then, as mentioned before, it is also take more effort and also time to start with. And this slide might feel like a little bit of a recap of what I've been describing so far. But again, at the center of reinforcement learning is, of course, the interaction loop, which is the cycle of state, action, and reward. And as I hope that everyone gets from the previous 5 or 6 slides, it begins with the state, which is what the environment condition currently is, which is also what the agent sees. And then the agent takes an action based on the state and also its current understanding about the environment. And then the environment will then move into a next state while also giving a reward based on the previous action. And this of a combination of the environment, the agent, and the interaction loop is what allows the agent to improve its understanding and also what allows us to build an AI engineers for your specific purposes. And it will take a little bit more time, but in the next slide, I don't have a slide for that one, but we'll move on into kind of a more concrete example, which I'm trying to do so now. I'll stop sharing and we'll try to share my other window. Can you guys confirm if it's seen? Okay.
Yes, we can see clearly.
Thank you. So I think I have an example in one of the slides that telling you guys that environment needs to have two main functions, which is the reset here, and also the step in which the environment will move based on the action that the agent selected. And I will not going to write the code for now because it's basically prepared already for the webinar. But for this example, it's basically a very simple example of an agent that needs to move to the right. Basically, the only objective for the agent is just to move to the right, but it has an option to move to the left. And we'll start the training for now. I'm sorry, I'm not in the right folder. Okay. So, whoops. I think there is some. Yeah, I encounter some technical issues. Sorry for that, but I'm not going to be able to show you this. Apologize, but I have other thing prepared as a backup. And this is going to be an example on how I can kind of observe the behavior of agents during the training, which basically to make sure that the agents is behaving as I intended it to do so. And there are a lot of things that I can observe here, such as the episode return max or episode return mean, which indicates how well the average returns during the training. And the ideal numbers is, of course, to increase over time, which is the current agent managed to do so. But there is also other important aspects as a trainer to see, not only increasing number of reward or episode return. We could also hope for a lower loss like this one, or even some other parameters that we can see, and then we can optimize later on if it's something that we didn't expect it to be. But again, apologize for the technical issue, but we're going back to the slides, and this time I've prepared. Can you see the slides now? I hope so. And I've prepared also an example of our train agent or EDA that managed to to trip during a tripping operation. And before I play the video, I would like to ask you to focus primarily on the right-hand side of the plot, which is labeled the ECD profile, or what we call it equivalent circulating density, which is during a drilling and tripping operation. Maintaining this ECD within the safe limits is very critical, because too low, it will risk an influx or collapse, while too high, it will risk fracturing the formation itself that we're trying to drill. And the shaded radian represent the safe operating window that we set beforehand. And the goal of the agent is, of course, to do the tripping operation while keeping the pressure profile inside this window at all times. So no tolerance on going outside of it. And in this video, we are comparing two different agents. The blue line, which is controlled by our train agent EDA, while the red line shows basically a random policy, which is an untrained baseline. And I'm going to play the video now. And at some point, the red line will frequently go outside of this pressure window that we set, but which could lead to a very serious well control issues. While in contrast, EDA in the blue line, which is our train agent, stays consistently within the bounds, which shows that she adapts to the objective that I set, but also considering all the physics behind the tripping operation itself, because we train it using the well sim environment that I've mentioned before. And for the second example, I've also prepared the drilling case. While in the previous video, I showing you a comparison between EDA and a random policy. But in this video, I'm showing you or comparing EDA with a real drilling case, which is executed by a real human engineer. And what you're seeing here is side-by-side view of a 3D simulation, visualizing the wellbore during active drilling. And again, I'm going to ask you to focus on something specific, which is the color around the drilling assembly on the bottom side of the plot. And there will be a color that will represent what we call a cutting concentration, which is a variable affecting how clean the hole is during drilling. And in this video, lighter colors will mean lower cutting concentration, which generally indicates better hole cleaning. And that's very important during drilling, especially in relatively horizontal section, because it could lead to, again, some well issues such as stuck pipe and other hazards. And yeah, on the left side is from what our train agent EDA does, and it leads to a lighter color or yellow color in in cutting concentration, while on the other hand, the right-hand side has a darker colors.
Yeah, Rasti, we're starting to run out of time, so
yeah. So I'm going to say one more sentence. While these two examples might be clear to you or not, but I'm trying to say that reinforcement learning or AI engineers, by building one of them or more of them, we're not just trying to automate control or playing with controls, but we're showing that AI agents trained using reinforcement learning can match or even exceed the human level decision quality in complex and high stakes operation. And it's what makes a combination of AI or a reinforcement learning in this case in wet physics is very powerful moving forward. So thank you.
Thank you so much. Gee, do we have time for one question?
Yeah, I think you guys realize this is so complicated that we cannot cover everything in one webinar, but we were trying to share all we have so far, what we learned during developing AI-powered engineers to you guys. So I guess we have a few questions here in the Q&A, but we can only pick one, probably the first one. Thanks for the good presentation, Resi. As you mentioned, you can either choose a open source reinforcement learning library or build your own reinforcement learning algorithms from EDA. What do you guys choose and why? Resi, maybe you can take this one.
Yes, thank you, G, and thank you for the questions. Yeah, as I mentioned, there are two basically different paths on choosing on how to start building your AI agents. And what we choose as a team is that we start with the open source library, in the sense that it makes us start a little bit early, because building one will go through a lot of process of understanding the concepts, and also playing with the tools that we think we need or we don't think we need. But with the open source library, we basically can nitpick what we want to use or what we don't want to use from them. But basically, it again back to the team choices. But eventually, it leads us to start a little bit earlier than others, and then we can then adjust in the midway. So yeah.
Yes. Okay, thank you so much, Asi. Thank you, all of you. And this wraps up today's session. And the recording and the slides will be sent out to you after the session. And I hope we see you guys again soon for our next webinar. Not going to take more of your time. Thank you so much. Thank you so much. Bye.
Thanks, everyone.